on that. You will meet some new minerals in terms of things like accessories, and that's fine. Make sure you record those. Really what we do about, though, for the rest of the course is to look at, it's more about textures of the rock. It's the relationship between the minerals, like that orthopyroxene overgrowing the olivine in the slide that we just looked at. A problem that crops up all the time is the problem that cropped up in that slide in the prac test, is people mistaking an overgrowth for an alteration. Actually, let me just put that back with the olivine. With that green stuff, it's in and around the olivines. Let's just zoom in on that one.
With rolling.
Now, a hornblende will overgrow things like olivines and pyroxenes, but it looks quite different to that. I mean, the big hint with this one, of course, is that it's the alterations coming in along the fractures in the olivine. So the olivine's got the conchoidal fracture, fluid seeps in there, and the olivine becomes quite unhappy. In this case, it's altering to that green gunk that's there. Let's have a closer look at the green gunk, and you'll see. Let's just turn the light up a bit. You'll see that it's not one grain. Okay, quite a few people describe the pleocharism of it, and I'm struggling to see pleocharism there, but I guess you can in some cases see it, because what you're seeing there is fibres that are coming in from the edge of the fracture. Okay, there's a central bit here. If you cross the polars, you'll see that it doesn't all go extinct at once. They're all separate little tiny little needles that are all interlocking like that. That's a classic sign that it's a secondary phase. So it's happened well below the solidus, and it's just because of fluid creeping in along the cracks in the olivine and reacting with the olivine at lower temperature to form these things here. Now in this case, I'm not 100% sure what it is. I suspect it's a greenish coloured biotite, because this rock is so potassic. You would expect a potassium mineral as a secondary phase. This, in fact, I think I did analyse this in the electron microprobe, and it turned out to be a biotite, an unusual composition biotite. What it is doesn't really matter. It's important to recognise that it is secondary and not a hornblende that's overgrown the outside. If it was hornblende and it was just around the outside, let's go to the edge of the grain. Whoops. You would certainly see it around the margin of the grain like this, but it wouldn't be this fibrous structure. It would be optically continuous.
It does, eh?
You wouldn't have all separate grains. It would be one grain. It would all go extinct at once. It would all have the same birefringence. You wouldn't be able to see those fine needles inside it. Okay, so don't mistake alteration for overgrowth. The overgrowths happen during the magmatic stage. It's happened during the crystallization interval. This stuff here has happened below the solidus, and it's just hydrous, aqueous fluids altering the stuff, basically. So don't fall into the trap of mistaking those two. And when you look at it, I'm sort of suggesting here that you need to go into high power and have a closer look. Once you do that with this slide, you can see straight away that it's just a mass of interlocking crystals. I think I've written this up before. They call it a decussate aggregate. And that doesn't mean it doesn't swear. Decussate means that you've just got randomly oriented crystals. I'm assuming cussate means that they're aligned. I've never looked up what cussate means. So that's a fancy name for that one. I've handed out, while I'm on that, and this is out of the first edition of Winter. If you look at the second edition of Winter, there's 3 pages of textual terms. Some of these are quite important. Some of them are over the top, and it's just nomenclature gone mad. But some of them are useful. Poikilytic is a really useful term. Okay, so poikilytic is where you've had like the autoclase grains in this thing. Let's just go back to power. where you get early crystallising grains included in later ones. Okay, and they're the sort of textures you'll be using. So you've got the peroxanes and so on, and the biotite up here sitting inside the later autoclave grains, which are actually slightly bigger in size. But that's the sort of thing you're going to be using to help you with crystallisation orders. Okay, so inclusion relationships, to an extent, the habit, euhedral, subhedral, anhedral, but you've got to be a bit wary of that. The olivines in this, for example, are all rounded off. Let's go back to plain white. Because they're not particularly happy, olivines. They've actually reacted with the milk. So that over that relationship there, with the orthoperoxine growing around the outside of the olivine, so this is OPX. You can see the pinkish colour there, this is olivine. The olivine doesn't look happy at all. It's not a happy chappy.
Olivine's never happy.
No. Although in one of your Gabros, you'll find, hint, hint, that it is.
Happy olivine.
Which one?
Why does olivine become unhappy?
Yeah, because it
When it
reacts
gets
poorly
overgrown.
with everything else. Because it's got magnesium.
Yeah.
Gets
Not
hydrated.
so much temperature, it's milk composition is the clue. If there's too much water around, it's not happy, and that's what's caused the secondary alteration. But the main thing that's caused that switch to OPX crystallising is there's become too much silica in the melt. Okay, the melt has become oversaturated in silica, and olivine is not happy with that at all. It actually reacts with the melt. This isn't necessarily a direct precipitate from the melt. It's actually a reaction between the olivine and the melt that's produced the orthoperoxane there. And that's because the melt has gone over a certain silica saturation level. If it doesn't do that, if you've got a very low silica melt and you've got a silica undersaturated magma, the olivine remains happy and doesn't do that. Stays quite euhedral. That's a hint for one of your Gabros next week. Okay. Where was I going with that train? I thought I was talking about quickolytic, wasn't I? Okay.
I love that one.
So that's a really good example of using textures to say, yeah, olivine's definitely begun crystallising first and then orthoperoxine. What you can't do in a lot of cases, if you look at my example description there, and this one's quite similar to the slide I went through. I went through the monzonite slide, which is slide 11. Yeah, slide 11 out of the box, set down the back. That's the one I went through last week before the prac test. And ironically, it's not too different from this thing. The only difference was that this one didn't have any plagioclase. If you look at the back, here's my crystallisation order. So that's an interpretation. A couple of things about this description. Notice it's not just a list of minerals, it's a story. Okay, so you're extracting a history, a crystallisation history out of the rock, and you're telling a story. And in past years, that's been the main criticism of the Gabro pracs that have come in, is that people just give me a list of minerals instead of describing the textures as well. I've broken it up into paragraphs there, and there's a paragraph per mineral, but I've written a story around it. I'm not just saying this is the composition of the olivine and blah, blah, blah. It's, I've written it, and it describes, importantly, the relationship between orthoperoxine and the other minerals, between hornblende and the other minerals. Hornblende overgrowing the outside of augite. Okay, that's really important. And I think students get lost, they sort of can't see the forest for the trees, is the expression, when they're doing this sort of thing. So you need to identify your minerals first, but then think bigger picture. How do they relate to one another? Things like that are really important. When you're doing the crystallisation order, you can see I've done it like this, so it's like a bar chart. Doesn't matter which, you can do it horizontally if you like, it doesn't really matter. It's got liquidus and solidus. You should know those terms. So the liquidus is basically everything above the liquidus is everything's liquid. Below the solidus, everything's solid. So it's a crystallisation interval, and it might be several hundred degrees. Okay, importantly, minerals don't all begin crystallising at the liquidus. There's usually only 1 or 2 liquidus phases at the most. And why we do that, why you can't say, yep, olivine crystallised and then it stopped, and then pyroxene crystallised and then pyroxene stopped, and then plagioclase started and then it stopped, and then orthoclase started and then it went right to the end. You can't do that because minerals will crystallise at the same time. There will be a lot of co-crystallisation. There's a few, if you think about the composition of minerals, there's a few hints of where that's not possible. Okay, you won't get olivine and orthopyroxene crystallising at the same time because one's an intermediate composition. Remember, OPX is intermediate between olivine and quartz, for example. You won't get clinopyroxene and hornblende crystallising at the same time because they're very, very similar composition. The difference is water, essentially. So hornblende will often take over from clinopyroxene when the water content builds up too high. Just as here, the silica content has got too high and OPX has taken over from olivine. But other than that, most minerals, once they begin crystallising, will go to the bitter end. Okay? Anhydrous minerals won't necessarily, so orthopyroxene, you can see in this one, and augite have both stopped when the water content's got too high. Now, I haven't written that there, but that's the reason behind it. This is just observation. Both of the pyroxenes in that particular slide, and this isn't slide 11, it's a similar one. This is actually from, this is from Mount Dromedary down the south coast. It's a monzonite as well. Again, the water content's built up too high, and you can see the hydrous ferromagnesian phases have taken over. Hornblende and biotite have kicked in when the pyroxenes are faded out, and that's all down to the water content getting up too high in the magma. But once hornblende or biotite or plagioclase or orthoclase or quartz begin to crystallise, there's no reason in most cases that any of those are going to stop. They'll just go right to the bitter end. There's nothing to stop them. Occasionally with the feldspars you might have a melt that goes what they call hypersolvus and your 2 feldspars will be replaced by 1, but that's fairly uncommon. In fact, this is what here you probably call hypersolvus. There's no plagioclase in it because there's not much. Most of the calcium is being soaked up by the clinopyroxene that's in there. Okay, so that's why you'll see a lot of these, in fact the ones that I just rattled off. So, what's the one I've got there? Plagioclase, the feldspars, quartz, and any of the hydrous ferromagnesian phases, there's no reason that they would stop crystallising once they begin. So that's why we do it like this. We don't just do a list. First was olivine, second was pyroxene, blah, blah, blah. It's not like that. It's more complicated, just to make your life interesting. And it's all based on observations. So how you handle stuff is inclusion relationships like this. You've got to be a little bit careful because the inclusion relationships can sometimes lead you astray. Here's my green texture. I think I gave this example the other day. You might, for example, have a pyroxene grain that's a bit unhappy because the water content's built up too high, and you'll see that you can see that it may have like a prismatic shape to it, but it's got it's a bit chewed up. Okay, so it's reacted with the milk because the water content's got too high. It might have an overgrowth, a hornblende. Okay, and you'll see some grains like that on the side, and other grains you'll see hornblende inside the pyroxene, and you go, huh? How does that work? And that's the 2D, 3D problem. That happens when you just happen to have a section that's cut this way, and it does that. So you're looking down from there, and what you're seeing just there is hornblende apparently completely surrounded by clinopyroxene by ore job. So it's what you're seeing there, if you think in the third dimension of the is that they're just a little dish-shaped, and it might be coming up from the other way. They're just a little bit that's coating around the outside, and you just happen to have sectioned through the edge of a pyroxene grain, and it looks like that there's hornblende inside the pyroxene. If you think about geological processes, that will help you. I think it doesn't make sense that hornblende would be crystallising for pyroxene. It occasionally will happen in volcanic rocks. I just had a deja vu that I mentioned that to you last week or the week before. Occasionally you'll see that you might have hornblende with pyroxene around the outside of it in a volcanic rocks because eruption gets rid of the water. But that's relatively uncommon. You'll never see that in plutonic rocks. There's no reason that a magma would lose its water. Okay, so as I said, you're telling a story, essentially. And keep that in mind. There's one of the slides you're looking at today, the basalt. There's a description of it in the back of your book there. And it's only a couple of paragraphs. It's quite a simple one, that one. Because most basaltic rocks are fairly simple. Remember, they're the two P's. They're the pyroxene plagioclase rocks. You may or may not have olivine, and the other little bit of odd, you may or may not have quartz sometimes. So they're pretty simple. So it's what page is it on? Basalt description. Yeah. So you've actually got it on page 210, you've already got a description of slide 19 there. And you can see it's fairly brief. There's not a lot to say about basalts. Intermediate and felsic rocks are far more complicated. Okay, I think I might shut up at that point and let you get started looking at basalt and the dolerite, or the peridotite, which is where basalts come from. Yeah, they get melted from peridotite.
I'm gonna throw up. I swear to God.
Is it too tight? Just cut it.
No, it's just like, well, I've got a pair of scissors.
Why is it too dark?
Oh, just. She's having a reaction to how sexy I am.
If you want to have another look at these slides,
I hope Jared will.